Well as IUCAA Data Center. Today I'll be talking about parallel computing. So why exactly do you use parallel computing? How to implement it? We'll talk about a couple of technologies using which we can use available resources in our computer, or if you consider a big cluster kind of thing, how you can do that, how to write a code, and what are the advantages and disadvantages of it. So this would be, I would prefer this to be an interactive session. Means if you have any queries or doubt, you can feel free to stop me and ask it. So let's start with serial computing. What do I mean by serial computing? I'm assuming that all of you are familiar with C programming or any kind of programming. So I'll be talking with reference to C. So let's say if you compile a program, then an executable will be created. And when we execute that executable, what happens is whatever is written, each and every instructions will be decoded, and individual processor will execute the code instruction by instruction. Now let's assume, or that is the fact nowadays, every computer or laptop is coming with multiple cores. So when we are executing these instructions, only a single core is utilized and remaining cores are unutilized. So we are not making use of all the hardware which is available. So how to make use of that? Instead, let's assume the code is in such a way that the instruction can be executed independently. Let's take an example of adding to arrays. Okay. Now, if there are n elements, each array element can be added independently. Means, let's say a first element, you have to add first element with first element, second element with second element. That can happen concurrently. And if you have 4 processors available, then you can divide the job among the available processor. If array size is 100, then each processor can take up 25 additions, and ideally the execution should take 4 times lesser time to complete the execution and generate the results. So why to use parallel computing? First, to save time. That is the main advantage of parallel computing. Means if your code or problem statement is capable of developing it to massively parallel, then your performance should scale linearly up to something. So you will be able to solve larger problems. Now let's consider you have limited resources. Means there is some limitations on how much computing power each server or each workstation can have. So there are limitations to that. And ideally, what happens is we have 16 GB RAM or maximum 384 GB or something like that sometimes. And if your problem requires more RAM than whatever is available, then what you can do is you can divide your problem on multiple available compute nodes. Now, let's take an example. If you consider IUCAA computing cluster, it has 384 GB RAM. And now, if you have some problem which generates or which utilizes data of about a TB, means about a TB, you have a RAM requirement of about a terabyte. So instead of, if you try to solve it on single computer, it is not possible. Instead, what you can do is you can divide your problem on smaller chunks, not really 384 GB, you can subdivide it. One can go with even 64 GB also if you have multiple nodes available, and each node will perform its own operation, and once things are done, it can send it to the master node for further processing. So that way you will be able to solve a larger problem. Another thing is, let's say if you want to perform some simulations, some Monte Carlo simulation where you will be simulating n particles. So for that, of course, at some point you will see some limitations. You will not be able to proceed further. There could be some disk limitations or computing, or it will take several, means theoretically, if you can try to compute the theoretical computing speed, it will take several days or of the order of several months. So to reduce that time or to solve the larger problem, again you can divide it on among available multiple cores or multiple nodes and try to solve it. So provide the concurrency means you can solve many things concurrently and get the results done. And last is make use of underlying parallel. So as I said earlier in the figure which I showed, if you execute it, it will be using only a single core. And rather we utilize a multiple cores. As we have multiple cores, why not to use it and get the better performance. So processing can be Flynn's classical taxonomy. I'm quite sure many of you know this. The processing can be divided into four parts: single instruction on single data, single instruction on multiple data, multiple instruction on single data, multiple instruction on multiple data. This is the basic thing. So if you want to start with single instruction on single data, what happens is in this case, what happens? Let's take an example, take an array, and let's assume you have to calculate square of each element in array. So what will happen in single instruction of single data? Single instruction on single data. What will happen is each array element processed individually. Means it will process first element, second element, third element, and so on and so forth till all elements are completed. So this is basically single instruction on single data. So multiple instructions on single data. In this case, what you can do is if you have array and you want to compute the square of the individual array element as well as cube of the individual array element. So that we can perform this processing units. So this will be your data pool. This will be your processing unit 1, processing unit 2, and from where your instruction will come. One instruction will be about, let's say, square, and one instruction will be about cubing the individual array. So next will be multiple instructions on multiple data. So we have multiple data sets. On each data set, we will execute a different set of instructions. The processing unit will fetch the particular data set, will get the corresponding instruction for that. It will process that and pass back the results. So this will continue. And finally, single instruction on multiple data. So whatever processing generally will do, that goes into single instruction on multiple data. In 80% of the cases, we follow this. So we have a data set and we will be executing multiple instructions on that. Single instruction on multiple data sets. So let's say you have some instruction and you are trying to execute on various files. You read that data and try to execute on different number of files. So how one can achieve the parallelism? There are different types of parallelism, or different ways in which you can achieve the parallelism. So the first is mid-level parallelism. So where this basically goes into processor where whatever bits we provide or whatever instructions we provided, that again will be split at bit level, and each flip-flop will execute an instruction that is basically a bit level instruction. We do not have much control on that. So next is instruction level parallelism. In this, what happens is we divide our problem on set of instructions. As I said earlier, let's say if you want to add, so you can divide the instructions, means independent instructions, add, subtract, multiply. These kind of instructions we can divide, and each processor can take up a set of instructions and process it. Finally, task level parallelism. So in this case, what we do is instead of dividing at task level, instead of dividing at instruction level, we divide the problem at task level. Let's take an example of square. Square is a task, or cube. Cube is a task. So we divide this task, and each process will be responsible for executing one task. And again, in that case, what we can do is we can use single instructions on multiple. Means depending on the problem statement, we can decide how we want to execute this, and based on that, we can go. So then again, parallelism can be divided into multiple classes. Shared memory parallelism. So whatever laptops or computers we have with multiple cores, there we can implement this shared memory parallelism. In this case, whatever we have multiple CPU cores which are sharing a memory, and whatever process is running on this CPU can access or all these processes can access any part of the memory. Means let's say there is some location which is occupied by this CPU and this CPU want to access that. So that is possible as this is a shared memory, and this shared memory can again be classified as uniform shared memory and non-uniform shared memory. So that is based on the access available to individual CPU units. So it is uniformly available to all CPUs or all the cores, then it is uniform. And if it is given more to one CPU core or one core, then it is non-uniform. This is basically structure of our standard laptop or workstation. We have multiple cores and shared memory. So another thing is distributed memory, where what we have exactly is each CPU, we have multiple units of CPU and memory which are interconnected. So again, depending on the problem statement or what kind of, there are several type of networks. Means one can go with 10 Gbps speed. But again, so if you are working with some problems where your communication is higher, means let's say in this case, what will happen? We have some data in this memory and process is running on this CPU, and it want to access some data which is residing in which is with the process executing on this CPU. So it will not be directly able to access it as the case was in this thing. So they, in this case, one need to use some message passing interface, it's like OpenMP or IntelliMP, using which one can share the data. Now, if your network is not strong enough, then that communication may become a bottleneck. So currently, latest this interconnect is InfiniBand HDR, which can provide 200 Gbps throughput. Means one will be able to transfer the data with speed of 200 Gbps. And what we have in IUCAA is something called as InfiniBand HDR, which is capable of transferring 100 Gbps data between units. So this is the distributed network. Now we have something called as hybrid. In this case, what we have done is we have combined shared memory and distributed memory over the network. Means, so we have multiple CPU units which has access to some memory location, and these multiple units are interconnected using some network or some internet. So this is hybrid. And generally all compute clusters follow this kind of class or fall into this kind of class. Means there will be several CPU units will have access to some memory, and several such compute nodes will be interconnected using some network to transfer the data. And finally, there is something called as GPU computing. So if you consider our CPU, what we have is a limited number of arithmetic and logic, a cache memory, DRAM, and a control unit. So instead in GPU, what we have is we have n number of arithmetic and logic unit, a set of cache and a control unit, which will be controlling this arithmetic and logic, and finally DRAM. So this GPU computing is well suited. GPU computing is well suited for single instruction or multiple data kind of problems, where instruction is shared along this line. Means all arithmetic and logical unit share the instruction given by this controller. Similarly, this is true for all the things. So if you manage to divide your data across all these areas, then only one instruction will be shared. So this is the default mechanism of execution of the GPU computing, and one can use many available things like PyCUDA is there if you want to work with Python. There is CUDA C available to run it through C, and most of the routines like TensorFlow provides support to GPUs nowadays. So let's start with OpenMP, which allows us to make use of shared memory parallelism. So OpenMP stands for Open Specification for Multiprocessing. It is nothing but an API which allows us to create multiple threads. So as it is residing on a single, or it will be running on, even though it is running on multiple cores, it is using the same set of memory locations, and this will create multiple threads, not multiple processes. There is difference between threads and processes. A process will have a process ID, its own stack, its own heap, and several other parameters. In case of a thread, it is part of a process, subpart of the process, and it will share these parameters. Means it will share the process, whatever stack memory is available for that particular process, whatever heap memory is allocated for that particular process. It will share all those things, and a process can have multiple threads, and the OpenMP uses multiple threads for the execution. What this contains means how this API is designed, or what all the parts of this API is nothing but compiler directives. There will be a set of directives, or basically directives is nothing but a set of statements which one need to dump in the code. It will be there. There will be a random library routine. If you are using GNUC, by default, this routine will be available with you, and environment variable. If you want to control the number of threads, then you need to use a set of environment variables. Now, this API is available for C, C++, and Fortran. Most of the GNU versions supports it. Its implementation is available on Unix. Linux means almost all Linux platforms. Like you can use it in CentOS, RCAA, Debian-based systems like Ubuntu, or even if you consider Unix-based system, BSD-based system like Mac operating system, all Macs, Windows operating system. So it is extensively used in MATLAB, Mathematica, even for that reason. Ideal also by default provides support for multi-threading using OpenMP, and libraries like Intel Math Kernel Library, GNU Scientific Library. There, most of the part in these libraries is written using OpenMP, which make use of available resources. So, how OpenMP works? So, as I mentioned, it is based on thread base. So, where multiple thread share same memory region or share a set of memory. So here nothing is automatic. Means one need to. It's not like okay, you compile using some flag and your code will be executed in parallel. No. So one need to modify your code, or one need to write your code in such a way that it will be executed in parallel. So you can decide which part of the code or which portion of the code should be run it in parallel. So it should not happen. So it completely depends on you. A programmer has full control. Means how one can define the code at what point one should divide or divide it on multiple cores, and where it should join the processes and all. So sometimes it happens that some of the problems or some part of the problem is not well designed or well suited for parallel computing. In that case, you can simply run it on single core. So in OpenMP, what happens is generally there will be some serial region, and it will encounter a parallel region where we have specified that okay, it is from here the parallel block will start. Then master thread, which is the main thread of the process, it will execute the fork and create multiple thread group, and it will execute multiple threads simultaneously, complete the computational job. Once computational job is complete, then it will synchronize, all threads will synchronize, and parallel region will be terminated, or execution of the parallel region will be stopped, and it will continue using a single thread. So this operation is called as join, and creating multiple threads is called as fork. So once parallel region is started, master process will fork the multiple threads. Again, you can configure how many threads you want to fork. Means you can do based on your architecture. Let's say if you have 4 cores available in your machine, you can or you can create 4 processes. And once execution is complete, this synchronization, and it will join all the process. This is nothing but if you have some shared variable or uh, some other things which you want to merge, or if you want to perform some reduction kind of. I will talk about these things, working in the reduction and all that. So if you want to perform some reduction operation, it will perform towards the end, and the results will be carried forward first for master process, and it will run. So what is the code structure? So initially we include something called as om.h, which is the header file where all impaired things are defined, or definition of the pragmas is done. So this is a C code. We have a main function. Then we will have some declarations and some part of the serial code. Means if you want to declare some element or define or assign some values kind of thing, one can do it over here in the serial code. And then the actual parallel division will start, where this can be defined like this. So for now, just consider hash pragma oriented parallel. So whatever is given inside that, what is private, what is shared, I'll talk about it. So all those things will be executed in parallel with total number of available threads. And once execution is complete, it will come here and execute the serial. Now, how do I compile this code? So you can simply use GCC -f OpenMP. This tells the compiler that the code written in this file makes use of pragmas defined in omp.h. It performs the link. So if OpenMP hello docs. So let's try some of the examples. Just a second, I will share my screen. Okay, I hope you can see my screen. let's start with hello. So here studio.h, which is required for standard C, defines input and output. We'll have a main function where we have included omp.h, which is responsible for defining this pragma, or definition of this pragma is set over there. So currently what I have done is I have not, so total number of threads can be set in 3 ways. So what I will do is I will not set anything. Okay. So currently nothing is given over here. So I just defined hash pragma OLB parallel, means from there our parallel region should start, and parallel region is defined in this curly braces. And in this curly braces, what I'm doing is I am trying to get the thread ID and total available threads in that thread pool, and I'm just printing ID of that particular thread and total number of threads. So now let's try to ISSAA manager. Compiled and created an executable called as. So I have not defined any threads over here. Means I have not set any number. I want to see what it does. So it has taken the all available cores. This machine contains 32 cores, and it has taken all the cores. Total number of threads are 32. And if you see the execution, it is independent. Means sometimes, okay, 20th process is executing first, then 29th. It is not means we don't have control on this. Means it will execute sort of randomly kind of thing. Now, I don't want, as generally, let's assume this is a shared resource, and I don't want to use all the threads available. So what you can do is you can, first way to do this is you can.
Ajay sir,
Yes.
your screen is stuck, not moving.
Stop means just told you. Yes, I guess. Shall I stop and?
Yeah. Reshare.
Can you see it now?
No, yeah, it's visible.
Okay, sorry for that. So one can export. Let's repeat it. I will not change anything in it. So now it has used only 8 threads. So this is the one. This is one way without modifying your code to set total number of threads. OLP underscore num underscore threads. So whenever you execute your code, your compiler looks for whether this environment variable is set or not. If it is set, it decides. It takes that value for to create the total number of processes. If it is not set, it go inside the code and check whether something that is available or not. So if you want to set it inside the code, you can use something called as OMP set underscore num threads. So this will override whatever value you have set on your terminal. Now I have set 8 over here, and if I say 4 inside my code, it will override that value, and the function will have more precedence. It will use only 4. But in that case, you need to recompile your code. Let's see. Okay, so this has taken only 4. And third way, is while defining your parallel region, you can set the total number of threads. Hash pragma OMP parallel. Earlier we have given this statement. Hash pragma OMP parallel. So
Ajay,
yes.
Sorry to interrupt. Are you also do you intend to share something else? Because all we are seeing is a terminal. We are not seeing the source code. There was a message on the chat that the screen is not changing.
I shared my screen as well, my source code as well.
So we are not seeing that on the Zoom view. Okay, so maybe you've just shared the terminal from the Zoom share. Maybe you can share the whole screen so that we can see everything.
Okay, just give me a minute. I'll share the entire window.
Yes, thanks.
So yes. Can you see the source code now?
Yes, thanks.
I was under assumption that source code is visible.
No, so now it's fine, thanks.
Okay, fine. Okay, I will just repeat quickly. So this is stdio.h used for iOS. We have included something called as omp.h, which is where this all pragma definition for that is defined. We start with main, and initially what we have done is these statements were commented. So none of the parallel region was said. We were having this only pragma statement where, okay, I can just quickly repeat that. So currently I have not defined any no threads, means I have not said anything. So when I execute that, it took 8 threads because I exported it. If I don't export it, it will take the total number of available threads. But it will execute on total number of available cores, basically. So one can override it using by setting omp underscore num underscore threads. Now, alternatively, what one can do is one can decide in the code itself. Means, let's say you have some problem which gives best performance only with 4 threads. If you go with 8 threads, even though resources are available, your performance deteriorates. In that case, what you can do is you can set this thing inside your code itself. But the only thing is you need to recompile your code. If you want to change the total number of threads, so you need to recompile your code. So I recompiled it and I executed. Now it is running on your 4 threads. Okay, that is the second thing. Now what I will do is I will comment out this thing. I will hash pragma OMP parallel. It sets the parallel block. Means whatever is given in these 2 curly braces will be executed across the multiple threads and using multiple threads. And here we are getting the thread number, means each thread will be assigned an unique ID. So we are getting that thread number and we are trying to get the total number of available threads, and we are just printing total number thread ID and number of threads. So I will comment out this region, and what one can do is one can set total number of threads for a specific parallel region. So we can have multiple parallel regions. Means once this is done, I can have over here some serial code. Let's say some file operation. I am reading some data for some file, and then again I can define a new parallel region. And here I can set num threads like 16. So this region I need only 4 threads because my problem is gives, let's say for some reason my problem gives best performance with 4 threads, and here I don't have that bottleneck. In next region, there I can use whatever resources are available. So you can define it over here, or after executing the serial code, you can say OMP underscore set num threads before, and it will use 4 thread, whatever number of threads you have. So let's try to set it over here. OMP thread set is not defined, and I will recompile the code and execute it, and it has executed on 4 threads. So this was basic hello world kind of thing. Now these threads are executing, and I don't want to start the next process until the last thing is last process has completed the execution. Means it is thread load is not uniform. Let's consider that scenario. Means let's say first thread will take only a few seconds. Second thread will take, let's say, about 100 seconds. Third thread will take, let's say, about 140 seconds or 150 seconds. And before executing the next instruction, you want to stop until all threads come to a specific region, and then only you want to execute this. That you can do using barrier. So what I have done over here is, so this is parallel, and I have set 4 threads, and then this TID represent the thread number. Now, if you consider the 0th process or 0th thread, the sleep interval for 0th process is 0. So ideally, it should not stop. So for 1, it is 1 second. For 2, it is 2 seconds, and for 3, it is 3 seconds. So the output should come like 0, 1, 2, and 3. Okay. So without giving any barrier, let's try to. So it is 0, 1, 2, 3, and it is stopping in between because there is a sleep with thread ID. Now I don't want to do that. I want to print this statement once processing for all threads is done. So that can be achieved by using barrier. So 0th process will complete its sleep statement. It will come here, it will say, okay, barrier is given, so it will not execute the next statement. It will wait for other processes. Let's see. So none of the thread ID is printed, and it has printed everything simultaneously. So this is barrier. So let's go to slide again. Now you have set the code, you know how to get the thread ID, and how to get the thread ID, how to get the total number of available processes, how to stop, how to define the total number of available threads, or how to configure it, how it can be specific to a block, specific to a code. Now there is some scenario where what you want to do is you don't want to share any variable. So what you want is each thread should have its own copy of the data. So you can define that using something called as private. So hash pragma OMP parallel, you can define a private thing, and whatever variables you want to make a private. Means let's say if there are some variables like var1, var2, and you want each thread should create its own copy of the private variable. So you can use private. So it will create a different variable, will initialize it to 0 or whatever default value of it. Where default means default given by the compiler, not by the code, and it will create an instance. Now, if you want to perform some initialization on that, so you can define your variable as first value. Means the whatever is the first value assigned to it, it will take across the it will take the value throughout the code, And once your execution is done, whatever is the last value is now there. If you want to take that, you can define your variable as last private. So it gives the last value of the or last updated value among the all threads. It will take that. And if you want to share some uh, memory location, you can use shared flag. Similarly, you can define shared somewhere, use that. And reduction is some operation which we'll see in some time. Let's go to the code. Is the terminal visible?
Yes, sir. Okay. So again, some standard things, main function and all that. So I defined a variable called as first private, last private, which is initialized to 0, private, which is initialized to 100, and some I. Okay. One more thing. If you want to execute your loop in parallel, so what you can do is, let's say you have some for loop, it is very straightforward. And if you want to run it in parallel, so you can simply add hash pragma omp parallel for before the loop, and you compile your code using -f open. So if you do that, your loop will be automatically executed using a number of or whatever threads you have set, it will be executed using those many threads. That job division will be done automatically. You don't need to worry about it. Means which operation or whatever instructions are there. So it will be evenly divided among the available threads. Means if it is 10 and if you say let's say five cores or 5 threads, then each thread will take 2 iterations and will continue. So here I started the parallel region, defined something called as private and first private, because private will create a new copy of this variable private for all the threads and will initialize to default value, which for integer it will see it will be 0. And first private, I don't want to set it to 0, I want to carry this value, initialize with 10. So that's why I set it first private. And after the execution, I want to get the value for the private. So do the last private. So let me just enter this code. Okay. Let's create this variable. And this private has initially 0 value, and I have performed some operations over there. I have added ID of the individual process to this variable before printing it. So it has given those values, and towards the end, I have printed the private value, so which is set to 100. And first private, I have defined your private variable as first private. So it has just carried the default value which is set in the code. So it has used the value 10 and continued with that. And when private has given the value of the last iteration. This is about the private. Now, I hope this is clear. Any doubts about this? What are your code till now? Okay. If not, then what we will do is we will see the last thing called as reduction. So let's say you have executed something and your results
you have performed sum, and just let's say if you have an array of 100 elements, you are working with 4 threads. So in principle, what each core can process or perform summation of 25 elements. You have done that, but each process doesn't have the full value. Means it doesn't have sum for all 100 elements. What it has is only summation for only 25 elements. You don't want that. Your aim is to get summation for 100 elements. So what you can do is you can perform something called as reduction. So you have executed a for loop, you have performed a summation. So each process will perform, let's see, for simplicity, consider that rank 0 or thread 0 will process first 25 elements. Thread 1 will process something, let's say, from 25 to 50. Thread, next thread will perform from 50 to 75, and the last thread will perform 75 to 100. 0, 1, 2, 3, or 1, 2, 3, 4. We can so in OpenMP by default it will be 0 based analysis. Let's stick to that for now. So it will be 0, 1, 2, 3. Now 0th process will have summation for first 25th element. First process will have summation for next chunk, which is like 25 to 50, and so on and so forth. So if you want to specify that after computing the local sum, that will be local sum for each process, or for each thread. After computing that sum, what we want to do is we want to get the final sum, and one can simply do that by using the reduction operator. Here we will define that the reduction operator is summation. I want to perform, so multiple operators can be used. So one can use multiplication, division, and not that kind of thing. One can also use it arithmetic, binary operations. All those things are available. So here I have performed a summation operation. I have said that okay, reduce this to a sum variable, and finally bring this. And so here I just utilize it to n, means ith element I will contain value I. So it is executed and got some value for 150, which is so first summation of first 99. It goes from 0 to 99. It uses 0 based classes. So how to use this in a problem means what I have showed over here is basically some bits and bytes, some pieces of the code. So private provides a functionality where one can take default initialized values. Reduction operator can be used to reduce the values, or for loop can be used to divide it across multiple processors. So we'll take an example of simulating a pi value. So here what we are doing is we are simulating some random numbers. Okay. Here we have defined a parallel region where we have these variables. I will just explain the logic. I will not go into all details. That may not be possible actually. So, we have defined a set of variables, and we have some shared variables. So here for computing pi, what we are doing is we are simulating points inside a circle and outside the circle, and basically dividing them by 4 to get the value of the pi, means total number 4 into total number of the points which are inside the circle divided by the total number of points, total number of simulated points, and we will be simulating this large number. Those many iterations will be there.
So we are getting a thread ID. Here we are setting we are setting the sync for random numbers. We are getting the total number of threads. We are defining the start and end. So ID to sub n. Sub n is nothing but total number of available processes. Our number, how many iterations we want to perform, divided by total number of available threads. And if you just make it smaller, it will be for rank 0, it will be 0 to sub n. For rank 1, it will be sub n to 1 plus 7 or rank plus 7. So we are basically deciding the start and end for individual job. Then we are running it in parallel. Means for each thread, it will be like start of that process or start of that thread to end of that thread. Then we are simulating random numbers. We are checking whether that lies inside the circle or not. And here this variable is shared. Means if it is shared, then it should not happen that two threads are accessing the same memory location simultaneously. That way our data may get corrupted. So once we define it as a critical, so only one thread can modify that memory location. So it is basically locking kind of thing. We are locking that variable before modifying, and we are computing the total points which are inside the circle, and finally the value of and printing the results. So let's try to execute it now. Okay, took around 6 seconds for the execution. Let's try to increase the threads. Let's see what happens, whether it gives some performance gain or not. So instead of this, maybe I should make it multiple. Okay, so let me change it to something like 10. So execution time has reduced to 1 from 6. So as we have increased the total number of threads or total number of cores on which the execution should happen, so this will continue up to certain level. Means it will not be like you keep on reducing the total number of keep on increasing the total number of threads and it will give the best performance. No, at some point it will saturate and you will not get better performance than that. So this is about the shared memory. Now if we consider our computer architecture, we are limited with RAM. We don't have infinite RAM, or we cannot have infinite processors or infinite cores in our machine or our computer. So there is some limitations, and that limitation will affect your performance. So if you want to overcome that, one need to rely on hybrid kind of architecture where shared memory and distributed memory is combined. So that can be achieved using computer clusters. So we have some cores, some RAM which are interconnected. So multiple nodes which are interconnected with each other, and that can be done using OpenMPI. So before going to that, I'll just tell what we have at IUCAA. We have a high performance computing cluster called Pegasus. It contains 2 head nodes, which is basically to run a job scheduler.
We have login nodes. These head nodes and login nodes and graphics node. This works in active passive mode. So at a given time, only one node will be available. So this ensures that when if something goes wrong with one node, another node will take up, and cluster will not be. It will not affect. It will not affect the login or any other functionality on the cluster. So we have graphics node which contains Tesla P40 GPU card, which is basically you have performed some simulations, you got some result, now you want to perform some visualization. It is dedicated for that. There are two such nodes and contains all kind of things like starting from ideal, MATLAB, Mathematica, then Python, various version of it. We have 60 compute nodes. The compute node has 32 cores each, and the total number of cores is 1920. The total number of the available RAM on compute node is 384 GB. This is the total. About 2 TB RAM is available. These compute nodes are connected using InfiniBand media, which is an interconnector network which is capable of transferring 100 Gbps per gigabit, not byte, Gbps per second. And as a scheduler, we are using something called as portable batch system, which provides several functionalities, starting from provides web-based user interface for job submission, and there are other things which allows job submission. It provides queue-based policies where based on the requirement, job will be submitted and jobs will be queued. It contains 1 petabyte of paper storage, and total theoretical computing speed of this cluster is 93.9. And now, if you want to use distributed memory kind of thing, one need to rely on something called as message passing interface, which is MPI. And there are several implementations of MPI: Intel MPI, Open MPI, and Platform MPI. It can be used from C, Python, Fortran, various things like that. So tomorrow we'll see about how to implement the codes in MPI, some basic functionalities in the MPI. So starting from what is the MPI code structure, how one can implement, one can do their job using MPI. So for now we'll stop. I will be happy to take questions. Okay. Hello. Hello. Hello.
Yes, sir.
So if you have any questions, you can ask.
Ajay, you just have a look at the participants tab and see if someone has raised a hand. So I see that Neil Vadadaria. So you can unmute them and take the Q&A.
Okay. Actually, I'm unable to unmute.
I would like to point out that your screen was not visible for the last 5 to 7 minutes.
Okay. So it was not visible.
Yes, sir. We were seeing a blank screen while you were discussing parallel computing on other platforms.
I'm not sure why it is. You're talking about after this computer cluster?
Sir, when I lost your screen, you were coding in C.
Was that problem for everyone?
Yes, sir. Many participants have put this in chat.
Okay. Do you want me to explain that again?
Yes, sir.
Okay. So, I guess have you seen this thing where I was simulating value of pi?
Hello? Yes, sir. Yes, sir.
Okay, I'll start with this. I'll explain this again. Okay. So please interrupt me if you lose your, if it is blank again. Just stop me in between because I'm not seeing these chat messages.
Actually, we cannot unmute ourselves without your permission.
Sagar.
Yes, sir.
Screen blank झाली तर फक्त immediately सांगशील.
Oh.
Okay. So what I'll explain this again. Here, what we are doing is we are simulating value of pi. So what we are doing is we are simulating the number of points on a plane, and we have taken a unit circle, and we are computing total number of points inside the circle and outside the circle. So we are simulating for this Yan value and what we will counter it. So as mentioned earlier, we are defining a parallel region, and we are defining a set of private variables. So ID, number of threads, start, end for the individual thread value, and we have some shared values as well, which will be used by all the threads. So here, what we are doing is getting the thread ID, initializing the seed for random numbers. We are getting the total number of available threads, and we are computing the total portion or total part which each thread should complete. Earlier we were in example we have taken 100 elements and we were having 4 processors, so that each processor was each thread was responsible for working with 25 elements. So in same fashion we are computing the portion which each thread should process, and based on that we are defining start and end. Means first process will go from 0 to the total number of elements which you have saved in 7. The next should go to 7 to 1 into 1 plus 7, and it will continue with that. And then each thread will start from its order. Local start has been defined for that to local end, and it will simulate random numbers, and it will generate 2 random numbers x and y. Based on that, it will check whether that point, specific point, lies inside the circle or not. If it is lies inside the circle, it will increment the temporary variable. Now, after that, this temporary variable is again shared. Means multiple threads has access to. It is possible that 2 threads can access this variable simultaneously, and that will correct the multiplication. So what we are doing over here is we are defining this variable as critical. Now, what do I mean by critical? Basically, if one thread is modifying value of that particular variable, no other thread will be able to modify its value. So we are putting some kind of lock on that temporary variable, and once write operation, in that case, one can read that value, but another thread can read that value, but will not be able to modify its value. So it will one thread can modify its value, and then finally we are just performing computations or dividing by total number of elements and multiplying it. So this will be done by in serial fashion, and we are just printing the time values and error associated with it. So just compile this program. For now, I'll be executing it with, let's say, three threads.
Sir, program is not visible.
Program or screen? So my screen is shared. Now can you see it?
No, computer cluster.
Not program. Yeah, some compilation statement and execution. Is that visible?
No.
No, sir.
I shared my entire. Can you see it?
No.
Yes, sir.
GCC-F OpenMP scene I.C. Can you see this?
is visible to me.
Okay.
Yes, sir. Yes, sir.
Okay. Fine. So just execute it. Let's see how long does it takes. Took about 2 minutes execution time and generated this parameter. Similarly, you can change the total number of threads and recompile the code. And then came to this computer cluster. So if you consider there will be some limitation of total number of maximum the amount of maximum memory which one computer can have, total number of maximum cores a computer can have. So what we do is we use some hybrid. The solution for that is to use hybrid architecture where there are multiple threads using some shared memory and those are interconnected using some interconnect. So we have a dedicated computing cluster at IUCAA. It has following configuration. It has 2 head nodes. Each head node contains 16 cores and 192 GB RAM. 2 login nodes, which has 384 GB RAM. So these nodes are in active passive mode, means at a given time, one node is in active state and another is in passive mode. If something goes wrong with one node, it will for the second node. There are 2 dedicated graphics nodes. Let's say if you perform some simulation, generate some data, and now you want to visualize it. For that, these graphics nodes are there. It contains NVIDIA Tesla P40 GPU card for visualization. We have 60 compute nodes. Each compute node has 32 cores and total number of cores are 1920. Each compute node has 384 GB RAM. Cumulative RAM is close to 2.3 terabyte. These nodes are connected using InfiniBand VDI, which is an interconnect capable of giving theoretical throughput of 100 Gbps, gigabits per second, and it is using something called as portable batch system as a scheduler, and it is equipped with 1 PB PFS storage and theoretical computing speed is 93.9 teraflops. And in order to transfer data from one process to another process, running on two independent compute nodes, one can use something called a message passing interface. And there are several implementations of MPA available, like Intel MPA and Platform MPA, Open MPA. And tomorrow we will see how to write codes in MPA, what is the structure or architecture of MPA, and how one can effectively use multiple compute nodes for this. We'll stop share now. Yeah. If you have any questions, you can take this. No, then you can stop.